So whenever we have digital communications or communications in general going on, then there's always the presence of noise, because noise distorts the transmission. And as seen in this little example, as long as the noise excursions are small, that's not a big problem, because we can easily identify where these points originally came from and thus decode our data with a high level of precision. However, what happens is that really we are wasting a lot of energy, a lot of resources. And it turns out that it's actually better from a theoretical point of view to allow more noise. Allowing more noise is synonymous with allowing for less power and using less transmission power. As soon as more noise is present in our system, we will experience errors occurring, and we'll have to have a way of controlling the occurrence of these errors. So it has been known, of course, since the early days of the computer age, that something like parity check coding, as shown in this slide, will allow you to identify an error, a single error occurring in any one of either the information bits or the parity bits. The only problem is, we can only identify that an error happened among a set of bits that we identify, but there is no immediate way of rectifying that situation. So it was realized a little later on that if we in fact take a large number of such parity checks and sort of interweave them into what looks like a very complicated network of really parity checks and these information variables connected through these check connections that make up that network, that these sets of connections, these sets of parity checks can actually correct errors as well, and they turn out to be extremely powerful error correcting and error control mechanisms. This was already known in the early 60s, in fact, and was pioneered by Robert Gallagher at MIT, however became popular only in the 90s when, shall we say, computer technologies and algorithms caught up with the huge demands of processing that was typically required. I'll give you an example of how this works. And this particular illustration just shows the errors only. We assume that two symbols are in error. They broadcast, all of the symbols broadcast their messages, and the errors are in red. You will notice that as the errors will hit the parity check nodes, it apparently gets multiplied into more errors because the check doesn't a priori know which symbols are wrong. Nonetheless, because of this network being distributed, being large, the errors get distributed all over the network and thus enable correction at the variable nodes. In fact, the nodes at the top simply take a majority vote or some kind of consensus measure as to what the different message paths are sending into the node. And in this case, we simply do a majority vote, and you'll see that all of these errors that happen in the process will eventually be corrected. The process by which this happens is an iterative process. It is a correcting method that goes back and forth between the nodes. It is an interesting algorithm in the sense that it's completely disjoint. It is not a localized algorithm. It's a localized algorithm in the sense that we have a large number of small processing nodes that then communicate their results. It's not a global algorithm that has to be run, and hence it's very scalable. Typical such networks are of the order of thousands of nodes or tens of thousands of nodes. That brings me to the next point, which is that the precise analysis of what happens inside this network, of course, for each node becomes very cumbersome and cannot be carried out very easily directly. So what we do is we look at the network as a whole, and we look at statistical properties of the signals across the network. In order to do that, I have on the right-hand side what is known as a protograph. So you've seen that I sort of flip the graph and look on it sort of from the side, so that all nodes are collapsed into a single proto-node. And the connections in between represent the collective of all the connections between all of these round nodes and all of the check nodes, so all of the variable bits and all of the check bits. And instead of measuring individual lines and individual messages and keeping track of those, I look at statistical properties of those messages. So I do a statistic analysis of the network. The parameter that I'm looking at can be the error probability, so the probability that any one of these messages is wrong or is erroneous. It can be a signal-to-noise ratio measure. It can be a variance measure. There's various different measures have been used in the past and are being used to analyze these networks. So what we see in the middle there is basically the analysis system with the where the statistical parameter at time I is being computed from the statistical parameter at the previous iteration or at the previous cycle. And we can thus arrive at the fairly simple, or at least simple-looking statistical dynamical equation that connects the current value with the previous value, driven by the parameter, in this case the epsilon, which is the error probability in this case. We then obtain a curve that describes this relationship, and the iterations progress through this curve basically by being reflected at the 45-degree axis and migrate from a starting point through the iterations, and in this particular case through the iterations all the way down to 0. So our fixed point is the point 0, which would signify no errors statistically, on average no errors, which would describe convergence of this particular code. Now these codes are very powerful. They have made it into a number of standards, and this slide here shows you the performance of these codes called low density parity check codes, or LDPC codes, compared to the theoretically possible limits of transmission. The blue line gives you the capacity limit, or the theoretically maximum rate versus power efficiency that is possible with binary signaling. And the dashed line will show you the same for unconstrained signaling, the so-called Shannon limit. So we see that while these systems are extremely powerful, they're not exactly reaching the limit precisely. And a lot of research has gone into figuring out how one can improve the performance, how one can actually push towards these theoretical limits in a more efficient way. And this particular question has in fact defied the community's efforts for a number of decades, and that's where spatial coupling comes in. So before we look at that, let's look at what I call multiple dynamical systems. So what we do here is we simply align a number of these systems, just 6 here, but in general there would be a large number, and you can think of them as being operated sequentially, one after the other, for example, and just look at them not as individual systems, but we look at them as a vector progression. So you can see that the iteration equation now is actually a vector equation. So xi contains all of the entries, basically all of the statistical parameters of all of these systems, of which, as I said, could be very many. In fact, in analysis, we often let at least one side go to infinity. So we have an infinite size vector recursion, or an infinite dynamical system. Now, clearly not much is happening here because this is not in any way different from what we have just seen, and this is not expected to behave any differently either. Coupling, however, now takes an additional twist to this story, in the sense that systems are not just connected within themselves, but they're also connected to their neighbors. And this particular graph here is just to illustrate that some of the connections of each of the nodes will in fact reach over to the neighbor on the right and reach over to the neighbor on the left. It is important that the connections are made in a random way, because each of these centerpieces represents a protograph, so represents a very large number of nodes. So the connections going left to right are fractions of edges that go from the center graph, so these center nodes, to the neighbor nodes. Coupling means I'm coupled to my neighbor in a very organized fashion, as shown here. In fact, one speaks of a coupling window, which is only one here because each node or each system is coupled only with its left and right neighbor. We'll see later on that we actually have to make this window larger in order to gain the desired performance. Now, if we only do this, again, not an awful lot is happening, and I'm assuming that the system is infinite to both sides, or it's ordered in a ring such that every protograph for every individual system sees exactly the same neighborhood. If that is the case, then I simply have a convergence of all of them following in parallel the convergence pattern that I would have for the individual system. Nothing changes. They all have the same behavior still, even if I couple them with their neighbors. Here comes the twist now. However, if I introduce a boundary condition to one side, the other side, in the middle somewhere, it doesn't really matter where I introduce the boundary condition, but if I introduce a boundary condition such that some of those, in this particular case, the left-hand side, some of those systems are tied down to known values. We can say, for example, all zeros would be a valid such value. They're tied down to known values. Then I have an asymmetry. I have a boundary condition introduced into this system. Interestingly enough, this has profound effects on the behavior of the system, as shown by this particular progression that I'm showing here. I have a convergence wave that develops, particularly from the left to the right. Mathematically, what happened is I've in fact destroyed the stable state that existed before I introduced the boundary condition. And I have made that particular stable state impossible to reach. The analysis of these systems, these coupled systems, is far from trivial, and we have to employ statistical convergence theory, in particular Lyapunov theory and other versions of nonlinear convergence theory, to in fact show the existence of these waves and show the new convergence region, i.e. the new values of parameters that can now be handled by the system. So I would like to close this short presentation with a couple of points. One is a physical analog to what is happening, and that is the instant freezing of supercooled water. If you have water that's frozen below the freezing point, it remains liquid until it receives a crystallization impetus, one could say, or until, in our case, some kind of an anchoring on the physical analog. The shock will do have the same effect. So the water will instantly freeze. So basically, you know, while it was in the liquid state, it was ready to, in fact, crystallize into solid ice, and that's a physical analog. So finally, I'd like to conclude with a graph that shows the potential of spatial coupling in another application, which is multiple access communications. And in multiple access communications, the task is to separate users that interfere at the receiver with using the same transmission resources. And without going into any details, you can see that iterative type communication systems that operate without coupling are limited in their performance. That's the middle line in between there. In fact, they flatten out. They have a fixed limit no matter what the SNR. Linear systems, likewise, are limited. They flatten out irrespective of the signal-to-noise ratio, irrespective basically of the noise level that's impinging on the system. If I couple the system, one can in fact show that the achievable rates will very closely approach the theoretical limit, known as the Shannon limit, the AWG and Shannon limit, and that's that curve at the top there that, you know, basically asymptotically approaches that Shannon limit. So this illustrates again, you know, the powerful effect that spatial coupling can have on iterative communication systems in general. Thank you.